Welcome to part 2 of Understanding Injection Molding. Today we are going to cover warpage in injection molded products. Warpage in injection molded products can be a real headache, but understanding its causes can make all the difference. It often stems from uneven cooling or variations in material properties. To tackle this, start by optimizing your mold design. Ensure uniform wall thickness to promote even cooling. Adjusting the cooling channels can also help maintain consistent temperatures throughout the mold. Warpage in injection molding occurs due to uneven shrinkage and residual stresses within the molded part. It can lead to dimensional inaccuracies and defects, making it a critical issue to control. Here are some key strategies to minimize warpage. Optimize mold design, uniform wall thickness. Keep walls consistent to prevent differential cooling rates and shrinkage. Proper gate placement. Position gates to ensure balanced filling and minimize stress concentration. Adequate venting. Prevent trapped air, which can cause inconsistent cooling and shrinkage. Control your processing parameters, injection pressure and speed. Optimize these settings to ensure uniform filling without excessive stress. Pack pressure and hold time. Apply sufficient pressure to compensate for material shrinkage during cooling. Cooling time. Ensure gradual and uniform cooling to prevent uneven shrinkage. Melt and mold temperature. Maintain an optimal balance to prevent excessive shrinkage or internal stresses. Choose the right polymer. Choose low warp materials. Some plastics, like fiber-reinforced polymers, reduce warpage due to better dimensional stability. Proper drying of material. Moisture can cause inconsistencies in shrinkage and warpage. Optimized part design. Use ribs. Instead of thick sections, this enhances strength while maintaining uniform cooling. Avoid sharp corners. Reduce stress concentration and prevent localized shrinkage issues. Optimize cooling. Use uniformed cooling channels. This ensures even heat dissipation. Advanced cooling channels that match the part's geometry can improve cooling efficiency. Warpage in injection molding can also be controlled using cooling fixtures and understanding molecular flow during processing. Understanding these factors can help in maintaining dimensional stability and reducing internal stresses. Cooling fixtures can help control the shape of a part as it cools, preventing excessive warpage. Holding the part in place ensures that it retains its intended geometry while cooling. This prevents uneven shrinkage by providing uniform support, reduces internal stresses and allows for gradual stress relaxation, reducing the risk of residual warping after ejection. This can be especially helpful when working with thin-walled or large flat parts like panels or housings. These products can greatly benefit from cooling fixtures to prevent bending or twisting. Use materials with good thermal conductivity like aluminum for effective heat dissipation. Apply uniform clamping pressure to avoid localized stress points. Ensure proper ventilation to allow gradual cooling without trapping heat. Consider automated cooling fixtures for high-precision applications. Molecular flow also plays a part in warpage. Molecular flow refers to how polymer chains orient and move during the injection process, affecting residual stresses and shrinkage. Proper control of molecular flow can significantly reduce warpage. Oriented polymer chains shrink. Differently, during injection, molecules align in the flow direction, leading to anisotropic shrinkage. Improper gate placement can cause uneven orientation, leading to warpage. Allowing polymer chains to relax gradually during cooling minimizes internal stresses. Optimize gate placement. Position gates to ensure uniform flow and balanced orientation. Injection speed and pack pressure also play a role in shrinkage that may cause warpage. Avoid excessive shear, which can cause uneven polymer alignment. Annealing or post-molding heat treatment. Slowly reheating and cooling parts can help polymer chains relax, reducing warpage. Glass or carbon fibers also reduce molecular orientation effects and improve dimensional stability. Warpage in injection molding is highly influenced by injection speed and cooling time. These factors directly affect how the material flows, cools, and shrinks, which in turn determines the final part's dimensional stability. High injection speed improves filling of thin-walled parts by reducing viscosity. Increases shear heating, which can lead to differential shrinkage and higher internal stresses. Can cause uneven molecular orientation, leading to anisotropic shrinkage and warping. May trap air, causing voids or inconsistent material density and burning. Low injection speed allows for more controlled and uniform flow, reducing differential shrinkage. Minimizes shear-induced stress, lowering the chances of warpage. Can lead to premature cooling in thin sections, resulting in flow hesitation and uneven part thickness. Use a moderate injection speed to balance shear stress and flow uniformity. Optimize the speed profile. Start with a higher speed to fill the mold quickly, then slow down near the end to reduce stress buildup. Consider material behavior. Some polymers require slower speeds to avoid orientation-induced warpage. Short cooling times can lead to premature ejection while the material is still soft, increasing deformation risk. This causes uneven shrinkage due to residual heat, leading to internal stresses and part distortion. This is more prominent in thick-walled parts where the core remains hot longer than the surface. Longer cooling times allow for more uniform shrinkage and stress relaxation, which will reduce warpage. This also helps maintain dimensional stability, especially in large or complex parts. This will also improve crystallization in semi-crystalline materials, making shrinkage more predictable. Ensure uniform cooling with proper mold design and conformal cooling channels. Do not eject the part too early. Allow it to solidify completely. Use gradual cooling rather than rapid cooling to reduce residual stresses. Balance cycle time. Excessively long cooling can reduce productivity without significantly improving quality. Let's look at mold temperature control systems and their effect on warpage. Mold temperature control is critical in injection molding because it directly influences cooling rates, material shrinkage, and residual stresses, all of which impact warpage. Proper temperature control ensures consistent part quality, reduced internal stresses, and better dimensional stability. Using higher mold temperatures. Slower cooling leads to more uniform shrinkage, reducing internal stresses. This helps in achieving better surface finish and molecular relaxation. It can increase cycle time, but improves dimensional stability. Useful for semi-crystalline materials. It allows proper crystallization and prevents inconsistent shrinkage. Lower mold temperatures. Rapid cooling increases internal stresses and uneven shrinkage, leading to warpage. This can improve cycle time but may cause non-uniform crystallization or frozen-in stresses. This may be useful for amorphous plastics, which require faster cooling to maintain stability. Water-based systems are the most commonly used for most thermoplastics, providing efficient heat removal. Alternative methods to reduce warpage in injection. Molding can go beyond optimizing processing parameters, mold design, and cooling systems. Several alternative approaches can be used to reduce warpage. These include material selection, advanced molding techniques, and specialized post-processing methods.